Statistical Rethinking, second edition, chapter 16. And we are going to do the first two medium difficult questions because they deal with the same, well, really same problem. So 16M1 and 16M2. Okay, so 16M1 first. All right, so we're going to modify the cylinder height model from the book, model 16.1, where at that time we set an exponent for height to be equal to 3, and we're going to make that 3 a free parameter and then refit the model and see what the estimate for that, for what that value is. So first we load the data just like we did in the book, and here I'm just copy pasting the model from the book. Okay, so we run that, and for our modifications, I am no longer taking height to be to the power of 3. I'm taking it to the power of r, and then I'm putting, so now r is a parameter, and I am putting r to be a normal distribution with mean 1 and standard deviation 1, and also setting a constraint to where r can't go lower than 1. And so, the idea is that weight is almost certainly increasing with height. And if r here is less than 1, then it would imply the other relationship. So I'm just assuming that height, all things being equal, is going to lead to heavier people. Okay, so we run this, and so the first thing we'll do is to look at this parameter r. So I have the Précis outputs for both models, although I guess I really just, if we're just going to look at r, I just need for the second model. And here is the exponent for r. And notice that it is, about 2.3 here. And that is different. It's different than 3. And in fact, the 89% credibility intervals don't include 3 at all. Okay. So that's interesting. And so then the next thing I want to do is to compare these two models using PSIS. And so when we compare these, it certainly looks like that free parameter is pulling its weight, right? So the PSIS score for the free parameter model is doing quite a bit better than the standard model or the original model where we had the exponent equal to 3. So now we're going to plot the posterior. So I'm just pulling posterior samples from both models here. And you can kind of look at the code to see what I've done here. It took me a little bit of trial and error to get it all together. So look at this. But when we finish, what we get is this. So I have the data plotted in blue, and in fact, let me just zoom in here. Okay. And now I have the new model plotted in black, and its errors in that gray, okay, or the HPDI in gray, and so you can kind of see it going up, and then the original model in red. And so it looks like that at these lower height values, that the new model is doing better, right? You see how it's, the black is much closer to the data than the red. But then as we go up into these higher heights, larger heights, taller heights, that probably the original model is doing better. So that's interesting. Okay. Now for 16M2, what we're asked to do is to assess a prior predictive simulation for the for these models, and then make some adjustments. Okay, so so I'm just explicating the priors here as we have them in the model, and then for R, because I used a truncated normal distribution. I mean, there might be cleverer ways to do this, but I just took a bunch of samples, twice what I normally take, with my 1, 1 priors, and then I just took the R values greater than 1 or greater than or equal to 1, and then just took the first 100 in SAMPs of those. Okay, so anyway, so we get all those. And then we're going to plot the priors for, and so for the original model, for that prior, I just take P, K, and sigma. But for the new model, remember I have a new free parameter, and that's R, so I have the same prior, but I put R in there. And then I go through and I just plot curves and just see how it looks against the data here. Okay, and we see that both models, they potentially are capturing what's going on in the data, but neither is doing that well. The bulk of their lines are very much under predicting the data, and so in other words, these curves in general just are not growing fast enough as height gets larger. So we're going to make some modifications, and there's endless modifications that you can make here. And so what I'm going to do is I'm going to increase this parameter for P, and I'm going to decrease this parameter for K. And you have to know a little bit about how the beta and exponential distributions are parameterized here. But bigger values, here in P are going to make bigger values. And then for the exponential distribution, the mean of the exponential distribution is 1 over the parameter. And so as you make the parameter smaller, then the values get larger. Okay, so but anyway, so I just basically do the same thing, just having made those two adjustments, and I plot them. And now you see that that both of them are really kind of moving back up, to where now the lines are growing. They have the potential to grow fast enough to capture the data. Some of them are rather extreme, but this is okay. That the data will very much pare that down. Really what we want to make sure of is that the prior believes that an appropriate fit is possible, or it's not skeptical of a appropriate fit. Okay, okay, we'll call that good.